Hey David.
How are you today?
I'm doing good. How are you?
Good. All right, so we left off at 25. Let's pick up at 26.
All right.
You got me.
What's the graph of y equal -6 look like?
It would be a horizontal line at -6.
Yeah.
Let me just get that one down.
Okay.
You want some of those 4 graphs, 2-page graphs? This one here. Want some of those? A couple? No?
But can I have another sheet of graph paper?
Yeah, you can take that one there. I'm going to make some copies of it, so you go right ahead.
What does x equal 2 look like?
It would be a vertical line at x2.
What's the slope of that vertical line?
It's undefined.
Okay. What was the slope of the horizontal line?
0.
Okay. Number 28, what's the easiest way to graph that?
Putting it in y equals mx plus b format.
Okay, I got no problem with that. Go ahead and do that.
So, would it be y equals 2x minus 6?
For some reason, you get the sign wrong repeatedly on these. I'm not quite sure why. In other words, if we start out with this, how do we get y by itself?
We minus 2x.
Okay, so how did that end up becoming plus 2x on the other side? In other words, is all we have to do, it's minus 2x. So even if I put it in mx plus b format, it's going to be minus 2x plus 6. Okay? The mistake I see repeatedly is this getting the sign wrong. We'll talk about that in a second. Maybe we can fix it. I'm not sure. Okay, so how do I graph that?
You start at you start at 6 on the y-axis, and then you go down to over 1 to the right.
Okay, yep. There's a slope of minus 2.
Now, about these positive and minus slopes, I always get these wrong. Like, which way is positive and which way is negative? Because I know sometimes, even if the slope is going down, it can still be a positive.
What's that slope?
So, positive.
What's that slope?
Negative.
That's positive. Positive is anything that goes from lower left to upper right. This is lower left down here. This is upper right.
And the negative is going
The opposite.
Yes.
Just think of the negative as anything else. In other words, if I have this, that is going from upper left to lower right.
How do you know where they start, David?
Okay.
You know, what's
Let's
the
start at
point
0.
here? Yeah.
Okay, there's a 0. Whoops. There is a 0 slope. Okay, I will start. There's a positive slope positive, 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 negative.
Okay, so what you're doing is you're using your x-axis as a reference point to whether it's going up or down?
Well, notice that if you look at any line, like that one, you can tell if it's positive or negative by the fact that this one goes from upper left to lower right. I can't think of, and this is negative, and this is negative, and this is negative, and then it gets 0.
You get it?
Okay, the moment you get on the other side of that, now you're going from lower left to upper right.
But if you're given, David, if you suppose you're given a test that has, you know, a 4-quarter graph, and it has a line on it, say the line that you drew right there, LL to UR.
Okay.
Well, let me put it this way. Suppose, like on one of the ones on the test, it isn't marked. Like if you go back to, I guess it was 25 or 24. 24, it's not marked.
Okay.
I guess I'm thinking, how do you know whether it starts at lower left and goes to upper right, or starts to upper right and goes down to lower left? Isn't it where you start your line?
It's not whether, in other words, this line here goes from lower left to upper right. It also goes from upper right to lower left.
Right.
So it's not the dual orientation that matters. Always start on the left.
Okay, so you always start on the left to make your determination.
In other words, the moment I hit 0, I'm going to middle left to middle right.
Okay, so you always start on your left, and then the moment you hit,
always orient. It's like reading words. Start from left to right. And if you go up to the right, that's positive.
Okay, and when you say hit 0, is that on the y-axis then?
Well, notice that when I say hit 0, I'm rotating this line. In other words, that's still positive. That's still positive. That is 0.
Okay, I want to make sure you definitely understand.
Notice that it was lower left to upper right, each one, until I hit the 0 one, the horizontal line. And then it's middle left to middle right. I wouldn't know how else to describe that. And the moment I go on the other side of that, now that's a negative slope, and that goes from upper left to lower right. So I guess the key is the L. If you're going L to U, always go from left to right. And if you go lower to upper, it's positive. If you go upper to lower, it's negative.
Okay, left to right, upper is positive, and then left to right. Okay.
You can't say just upper is positive. It's L to U is positive. Lower to upper is positive. Upper to lower is negative. And always go left to right. And then that's all you have to memorize, is that lower to upper is positive, upper to lower is negative.
Right. And basically you determine where that line starts because you're always starting from the left.
Well, the line actually starts at negative infinity. In other words, I'm never drawing the end of this line. Technically, I should put arrows on it so that you know that it extends both ways.
Right.
Okay?
But that's where it comes on your graph then, is when you start to your left, that's where it's, wherever it comes, positive, negative, or neutral.
Best way to handle this is, let me give him some test slopes. And I'm betting he's going to get every one of them right. Patrick, what's the slope of that? Negative or positive?
That's a positive.
It goes from U.
Oh, I
Comes
see.
in on the
L.
left and it goes down.
Oh, yeah, so it's a negative.
Okay.
Is this important? We want to make sure we have this nailed.
Absolutely. You definitely want to know these.
That's another negative.
Good. Because it goes from upper to lower. Now, if I alter it just slightly,
That'd be a positive.
because it goes from lower to upper. So as long as you think left to right, then the only thing you have to memorize is this L and U or U to L.
If it's upper, lower, and what? What's the straight line called? It's upper, lower, and the straight one is called what, David?
The horizontal one is 0.
Yeah, 0. Okay. So we got upper. You got up, down, and 0.
Yeah, pretty much.
Yeah.
In other words, this one goes from lower to upper. That makes it positive. In other words, L to U is greater than 0. U to L is less than 0. And it's all you have to always do is read left to right. Now, the only thing I don't like about this rule is the L can be mistaken for a left or a lower. But when I use it in this context, that's lower, that's upper. That's upper, that's lower. And you're always reading left to right. Okay, so let's go back a moment. I don't want to leave this problem unattended. So when you solve this, you got y equals minus 2x plus 6. In other words, all I did was move the 2x to the other side. And I don't know if that kind of thinking works for you or not, Patrick. It works really well for me, and it seems to save a step. When I go to do this algebra, I do not think this way. The way I think is I need to move this to the other side, and the moment I move anything to the other side, it changes its sign. So if I want to move the 2x to the other side, I just do that. Okay, now I have y equals 6 minus 2x, but I can rearrange that and put the x in front, minus 2x plus 6, and now I have it in mx plus b format. I'm going to start at 6. I'm going to have a negative 2 slope. Okay?
Okay.
That's one way to do this problem. Personally, I think there's an easier way, and let's talk about it. And the reason it's easier is you don't have to figure out slope. Remember I said yesterday that when a linear equation, which is what this is, it's the equation of a line, when it's in standard format, there's actually an easier way to graph it. And that's to figure out the y-intercept and the x-intercept. And when you do that, you don't have to worry about slope. What's the x-intercept? Where is this line going to cross the x-axis? What is y at the x-intercept equal to?
6. So
No, hold on,
0.
hold on. We're talking the x-axis, not the y-axis. In other words, any straight line usually goes through both axes. So there's always an x-intercept and there's always a y-intercept. How do I figure out the x-intercept?
You change the y to a 0, so it'd be 3.
Good. There's 1 point on my line. How do I figure out the y-intercept?
You do the same for the x, change to a 0.
So in other words, I don't have to translate this equation into y equal mx plus b format. I can figure out the y-intercept really easily by just setting x equal to 0. Now I have 2 points. 2 points make a straight line. I can graph that thing and I never had to figure out slope. So when you see an equation in standard format, always know that the easiest way to graph it is this way. It's not the only way to graph it. And, you know, you want to graph it whichever way you feel most comfortable. But I think it's useful to know multiple methods. I really do. Really fully understand a problem, I think you need to be able to look at it from multiple ways. Alright, while running on a treadmill, in 20 minutes you lose 2 pounds, and in 40 minutes you lose 4 pounds. What's the average rate of change?
Well, isn't the rate of change just the slope?
It is.
So you'd put
So if I were to graph this thing, and I put time on the horizontal axis, and your weight loss on the vertical axis, then at 20 minutes, you've lost 2 pounds, and at 40 minutes, you've lost 4 pounds. The average rate of change is that slope. That's why slope is so important, in case you're wondering, why they put so much emphasis on slope. Because it leads to all higher mathematics. And this is the first question I've seen you get that talks about it in terms of average rate of change. Calculus is all about instantaneous rate of change. In other words, calculus is all about slope. Only the slope at a point instead of over a range. So what is this slope?
it's 20 over 2, so.
Okay, slope is what again?
Rise over run.
All right, don't get them mixed up. What's the rise?
It's 2.
What's the run?
20.
So it's 2 over 20, not 20 over 2.
You're going to have to, when you do these problems, you're going to have to put rise over run down. I mean, write it down and then put it in. I think that's a good tip for you.
Well, I try to get students to remember slope as rise over run and forget all that more complicated stuff. Because if you remember rise over run, you can translate the rise. Well, the rise is y sub 2 minus y sub 1. The run is x sub 2 minus x sub 1. But it's easy after a few years. Go ahead, David.
He needs, what all I did is told him is that he needs to slow down and write down. When he gets a problem like this, he needs to put just over in the corner his rise over run, because for some reason when he does it in his head, he knows it, but he gets them inverse for some reason. Or if he had it notated, then he'll make sure he gets it right. So rise over
I
run.
suspect the reason he got it inversed was because there's a natural inclination to put the big number on top and the little number on the bottom.
Right.
And
But that won't cut it.
if it was 40 over 20 and this was 2 minutes to 4 minutes, he might have gotten it right. I don't know. But as long as you remember rise over run, you'll always get it. You won't get them mixed up. So the slope is 1/10. 1/10 what? What are the units on it?
pounds per minute?
Yeah. That's exactly what's happening, is you're losing 1/10 of a pound per minute. Were it only that easy? I don't know of any treadmill that gets you to lose 2 pounds per 20 minutes, but okay, they want us to solve this by graphing. We can approximate it online here. So our first order is to graph both lines. What's 2x plus 5?
That starts at 5. And then it goes up. Does it go down to over 1 to the right?
What kind of slope would that be?
Negative.
So
Down to over 1 to the left.
that's all you have to do. In other words, if you end up with the wrong slope, just make it go the other direction. Now, let's talk about this. You can go up or down. There's no right or wrong. If I wanted to go up 2, then I'd have to go to the right one. If I want to go down 2, I got to go to the left one. Either one results in the same line. Remember, this is a line that goes to infinity in both directions. Okay, how about the other one?
With that one, you'd start at -3.
Okay.
And then you'd go up 4 over 1 to the right.
Okay. So our intersection point is our solution. Now, that's not easy to figure out on my graph. In other words, I know this point is 5 and I know this point is -3. And let's see, we were going to go down 2 and 1, so that's -1. That must be +1. This solution looks to be at, if I had to guess, I would say x equal 2 and y maybe 8. That would be my guess based on my graph. If you were graphing this on grid paper, then you'd be able to just count up the squares and know exactly what your solution was. This is the drawback of a graphical solution, is it's not very precise because you have to approximate where this intersection point is. If I wanted to know exactly what my solution is, well, if y equals that and y equals that, then I set them equal to one another. And I get x equal 4. So I was way off in my approximation. And that's because you'll notice that this line I curved a little bit up. It's not quite straight. And I'm approximating everything else. So it's really easy to be off if you're actually trying to find your solution from a graph. So I'm not that fond of solving a system by graphing it. It's important that you understand that that is where the solution lies, is at their intersection point. But in terms of actually solving it, it's usually the worst way. Notice that I wasn't even able to approximate a reasonable solution. But algebraically, I came up with it in about 10 seconds. And if x is 4, y is 13 based on this. So the actual solution was x is 4, y is 13. All right.
So, but David, I just stepped out for a second. On this 30 then, wouldn't he go ahead then and do a chart that had X and Y and put in a number of points and then connect them together? Is that what we're doing based on this formula?
Yeah, it is. How he has to actually do it, I don't know. Do you have a graphing paper?
Oh, yeah.
And if you got this problem on a test, you would do it on graphing paper, right?
Yeah.
Okay. Well, on graphing paper, I'm not going to have any of these problems that I had when I did it. In other words, notice that my -1 is shorter than my distance to 1. That problem wouldn't exist on graphing paper. Also, I would use a straight edge to draw my lines, and I wouldn't have a curved line there. So all of the mistakes that I can make approximating it, you wouldn't make if you were doing it on graphing paper. And when you finished doing it on graphing paper and went to read this intersection point, you would see that it's very, very close to where X is 4 and Y is 13. This value is actually 13, and this value is actually 4.
But as for one of the things that she is big on is that he's required to show all of his work for each question. So for on that 30, what he would start off with is an XY chart that has if X is whatever number it is, Y is this number, then go down and get a number enough.
Well, really,
what
he needs to do, if he was taking a test, what he would do was plot the first line, graph it, and label it. That is Y equals 2X plus 5. Okay?
All right.
Graph the second line and label it. That is Y equals 4X minus 3. Those lines are going to intersect. If he uses a straight edge to draw these, he will get his intersection point. He will read the coordinates off of that, and they will be 4, 13. That's the way he solves it for this problem.
And you know how to solve each one of these equations? You do? Okay.
In other words, you wouldn't do the last step that I did, which was to solve it algebraically to find out what the real solution was. My graph is such that there's no way I'm going to come up with an accurate solution hand drawing it like this. When you do it on a test, you're not going to be hand drawing it. You're not going to draw a straight line with just your free hand. You're going to do it using a straight edge. And you're going to do it on grid paper.
Right.
Well, as long as you do it on grid paper and you use a straight edge and you're accurate enough, you'll find that these 2 points cross at where X is 4 and where Y is 13. And that's the way you would come up with your solution.
And Patrick, how do you solve this Y equals 2X plus 5? I mean, how do you solve that?
You start at 5.
You start at 5.
And then you go down to over 1.
Oh, down 2 and then over 1. So you have those down.
Yeah, he knows how to graph them. He knows how to graph each line. He did that properly.
All right, I just wanted to make sure, yeah, because I was out for a second. I just wanted to make sure that he's got the underlying basis to create the right kind of graph.
He definitely knows how to create the graph. And as long as he draws them accurately, wherever they intersect, that will be the solution. That's really all he needs to know for this question.
Okay, so that will help you. Okay. All right.
Okay.
So
now, this next question, I have 2 equations and 2 unknowns.
Is this 31?
Mm-hmm.
First of all, would we use substitution or elimination on this, and why?
Substitution?
Yeah, it gives us our choice. But remember, we want to use elimination when the thing is in standard format, when both equations are in standard format. We want to use substitution when you have one equation that's fully defined for one variable. Notice this is fully defined for y, which means I can take whatever it's equal to and substitute it into this equation. So how do I write my second equation now?
What do we, 2x plus 5x equals 14?
Proceed.
Right, so that would be 7x equals 14, and then x would equal 2.
And then what's y equal to? Remember, you always have to solve for both variables.
Plug it back in.
Okay, so then you just plug that back in. You plug 2 in. Wait.
Yeah.
Yeah. So you get 4 plus y equals 14. So
First
y
of
would
all,
equal 10.
First of all, plug it into the simplest equation to solve for y. Is this one, if I plug x, the value for x in, is it easier to solve there or is it easier to solve over here?
I'd say to the left.
Okay, so do that one. What's y equal to?
Y is equal to 10.
That's it. Always choose the easiest equation to solve for that second variable. And whenever you've used substitution, the easiest one is always going to be that one there. The one that was fully defined from the beginning. Okay. Now this one, before I write it out, am I going to use substitution or elimination?
You see this right?
32.
32.
You're going to use elimination.
Right. So therefore I'm going to write it like this. I'm going to write one above the other. They're both in standard format. So remember, I've decided I'm going to use elimination. So how do I get one of the variables to be eliminated? What do I have to do?
Well, one of them is eliminated right there, the y. Because it's plus and
Not
minus.
yet. In other words, it's not eliminated unless I'm adding the two equations. Remember, you can add or subtract equations. So I have to add these two equations in order to get the y variable to go away. It's not always adding. Sometimes you're subtracting. And it's important that you know which. In order to get 0y, I have to add these. I can't subtract them. Okay? So what else do you get besides 0y?
You get 7x equals 7.
So x is equal to,
What?
okay, and now solve for y. Which equation do you put it into?
You could put it into the bottom one.
I think that that's the easier one, so tell me what to write to solve for y.
You could do you could do 2 minus,
Hold on, what am I going to write in place of x?
1 minus 2y equals 4.
Okay, now solve that.
Plug it back in. No? Good.
No, you don't plug it in. You got to solve this equation for y. In other words, this now is a very simple algebraic equation. How do I solve it?
You take 2 times 1, which is 2,
Okay.
minus 2y equals 4.
Okay, now what?
You could minus 2.
Okay. Leaving what? Tell me what to write.
Okay, you'd have negative 2y equals 2.
Okay, last step.
Negative y equals 1.
Don't divide both sides by 2, divide both sides by negative 2.
So it would be y equals negative 1?
Yeah, in other words, this last step, always, there's no reason to divide it by 2 and then have to divide it by negative 1. Let's just divide it by negative 2, and that gets this entire coefficient to disappear. Okay, so y equals 2 over negative 2, which is negative 1. So our solution is x equal 1, y equal negative 1. All right, now we're dealing with inequalities. I did look at these questions, and these last 16 questions are quite a bit more difficult than the first 25. So I would suspect that we might not even get to 41 by the end of today. How do you graph an inequality?
You have to put it in y equals mx plus b format?
It's already in that format. You have to graph it as if it's an equation. So the first step is just graph it as if it's this. And then we'll deal with the inequality sign. So how do I graph y equals 3x minus 4?
You'd start at negative 4. Then you'd go up 3 over 1 to the right.
Okay. Now we deal with the fact that it's not an equation, it's an inequality. Which side of that line am I on to satisfy this inequality?
You have to be on the negative side.
Am I on this side number 1 or am I on this side number 2?
Number 1.
Yeah, and the way you figure it out is you always look to the y-axis. In other words, this says y is less than or equal. So all I have to do is look to the y-axis and find a point there that's less than or equal to this point. So there's a point, there's another point, there's another point. All of those points have to be on the correct side. So that's my shading. And that's the way you graph it, is to draw a line and shade one side or the other. Now, this line isn't always a solid line. If the problem was that y is merely less than 3x minus 4, then I would make this a dotted line. But doesn't affect the shading. The shading would still be done the same way. Always look to the y-axis to figure out which side to shade. Okay. 34 is an entirely new subject, and so is 35, and so is 36. 37 is very similar to 33. So let's do 37 next, so that we can not jump back and forth between subjects. Here we have two different inequalities. We have y is greater than or equal to minus 2x plus 4. And then we have this other thing that's not in terms of y, it's in standard format. Okay. Our goal is going to be to graph both of them and find the common area. In other words, we graph both of them, shade both of them, and wherever both of them are shaded at the same time, that's our solution. So let's graph number 1.
You'd start at 4.
Okay. Let's see, 1, 2, 3, 4. Okay.
Then you could go down to over 1 to the right.
Okay. So that. Is it a solid line or a dotted line?
It's up solid.
Which side of that line am I on?
You're on the left side.
Remember, look to the y-axis. What's this say?
Y is greater than or equal to.
Okay, so using only the y-axis, where is y greater than or equal to that line?
To the right.
Above. In other words, rather than using terminology left or right, which is very confusing, let's use terminology above or below, because we're always talking about the y-axis here. So we're never really talking left or right. We're always talking above or below. Well, if you tell me above that line, I'm going to go to the y-axis, I'm going to find a point above that line. That tells me that this is where I should shade. Okay? Now let's graph the second inequality. First of all, what do I have to do to it in order to graph it?
Put it in y equal mx plus b form.
Yeah. Or you could graph it the other way, which is to find an x and y intercept, because it's in standard format. But this is relatively easy to put into y mx plus b format. So what's the next line?
It would be y is greater than. Oh, you flip it.
Less than.
Oh,
Don't
sorry.
flip it. Remember, you only flip it if you are multiplying or dividing by a negative number. Never when you're adding or subtracting. And the only thing I have to do is what? What's my first step here?
You just add 2.
No, the 2's already over on the right. We want to leave it over there.
Oh, you add 3x.
Okay, so when I add 3x to both sides and put the x first, I get that. Now that's pretty easy to graph. Where do I start on that?
-2.
Okay. Slope?
You could go up 3 over 1 to the right.
Okay. Solid line or dotted line?
Dotted.
Above or below the dotted line?
Below.
Okay. So I'm going to use vertical stripes here to shade it. So the area of our graph that has both horizontal and vertical stripes is this area here. And that's your solution. Wherever you have both shadings. Okay?
All right.
All right.
What question was that? Was that 37?
That was 37, but we're going to go back to 34 now. In other words, I did 33 and then 37 because they're both very similar kind of problems.
Yep.
Now let's do 34. And 34 really opens up a whole area of math that we haven't talked about. And that is transformations. Now, I'm not sure why they're getting into transformations this early, because linear functions are not very good for illustrating transformations. It's only once you get into functions that are curved where transformations really, you can understand what they mean. When you have a straight line, you know, it doesn't, if I take a straight line like this and I move it to the right, it becomes this, but if I move it down, it also becomes this. So talking about transformations when you're talking about linear functions is not useful. In fact, it's probably confusing and harmful. And that's why they don't give you a function. They tell you what is the transformation if you have minus 1/3 of the function and then subtract 5. Do you know the answer to this, Patrick?
No, we didn't. I wasn't there when they covered transformations.
All right.
Those are complete.
So, what's the best way for me to cover it? Probably using the absolute value function, because they have two questions here on transformations. They have 34 and they have 36. Now, with the absolute value function, it kind of makes sense. We can talk about transformations because it's not a curved line, but it is a broken. It's a line that goes in two different directions. It has two different slopes. Okay? This function here, and I'll use the f of x terminology, is the absolute value of x. Transformations are all about taking your elementary functions and moving them around on the xy graph. Okay? If this is my absolute value function, well, I can do a lot of things to this function. I can move it to the right. I can move it to the left. I can move it down. I can move it up. I can move it to the right and move it down. I can reflect it over the x-axis. I can reflect it over the y-axis. Notice it doesn't change when I reflect it over the y-axis. But if the function was over here and I reflected it over the y-axis, it would become that. So, you understand what reflections do?
Yes.
Okay. Notice that when I took my straight line, if I move that 2 units to the right, it becomes that. But that's also 2 units down. In other words, if I took this straight line and moved it 2 units down, it gives me the same line as if I move it 2 units to the right. But that's only because it's a straight line. And that's why straight lines are not really good functions to illustrate transformations. There are 6 ways to transform a function. Let's list them.
How many, David?
6.
6? Okay.
There is reflection over x. There is reflection over y. And each one of these has a way of defining it using the f of x terminology. There is a reflection over x. There is a reflection over y. The other 4 are horizontal, left or right, that's how you accomplish that. And if you don't understand this yet, don't feel bad. I'll explain each one of these. There is vertical, up or down, and you get that by f of x plus some number. There is horizontal, stretch or squeeze. And you get that by doing this, multiplying the inside by some number. And finally, the last one is vertical, stretch or squeeze. And you get that by some number times the f of x. Notice that everything here is different. None of those are the same. Those are the only things you can do to a function in order to do a transformation of it. We're going to use the absolute value function to illustrate all of these. Okay, so let me move that out of the way. Our f of x is going to be the absolute value of x. And the graph on f of x equals absolute value of x is that. Do you understand what absolute value means?
A little bit.
It's not hard. What's the absolute value of that?
-5.
It's always the positive number.
Never negative.
What's the absolute value of 7? 7.
No.
What's the absolute value of -7?
7.
Okay. That's all there is to absolute value. The reason this is the graph of absolute value, notice, if x is 1, what is y? Or what is f of x? In other words, here's f of x equals absolute value of x. What is f of 1?
1.
What is f of 1 equal to?
It's equal to 1, isn't it?
Right. It's equal to the absolute value of 1, which is equal to 1. So if I go up here on my curve, there's 1 comma 1. In other words, when x is 1, y is 1. What's f of 2?
2.
Okay. I go up here to my curve. When x is 2, f of x is 2. What is f of minus 2?
2.
No? Oh, excuse me.
Oh.
Yeah, sorry. Absolutely. Well, if I go over here to my curve and I go to the minus 2, f of x is still 2. So that's why the curve looks like that. Looks like a V. Is that it doesn't matter what x is, f of x is always positive. F of minus 13 is 13. So it results in a curve like this, as opposed to a straight line which would keep going down, be like this. If I had f of x equal x, then f of minus 2 would be minus 2. So the absolute value function is slightly different, okay? And we're going to use it for a reason as our reference function. So let's talk about the first possible transformation, a reflection over the x-axis. Well, I've said that that means it's minus f of x. Well, that would be minus the absolute value of x. That looks like, I'm going to draw the transformation in dotted line and leave the original function there and illustrate each one of these with this original function. In fact, here, let me do this a little different so we have a little more room. Notice that it has a slope of -1 to the left of the y-axis, and it has a slope of +1 to the right. Okay? So that's f of x. Let me label it. F of x equals absolute value of x. So we talk about this translation. This would be the reflection, and this function is y equals negative f of x, or negative absolute value of x. If I lose you at any point, stop me and we'll back up. Okay?
All right.
If I wanted to take f of minus x, in other words, we've covered the reflection over the x-axis. Let's cover the reflection over the y-axis. Now, the reflection over the y-axis merely means we take this whole thing and rotate it about the y-axis instead of the x-axis. Well, you can see from this v that if I rotate it over the y-axis, I get the same function, right? You see why?
Yeah.
Doesn't change it at all. Well, this function here, the dotted line, is f of minus x, this right here, which in this case means what? What does f of minus x mean? What does it mean when I have something other than x in the parentheses? What do I do with it? Replace x with it. That's what it means. In other words, every single one of these things you see over here in my rectangle, we're going to do this process. For the third one, we're going to replace x with x minus h. That's how each of these transformations is best described. Is first of all by using the f of x notation instead of y, and describing them like I have described them over here. Now notice why f of x equaling the absolute value of negative x looks exactly the same as the absolute value of x. No matter what x is, f of x is going to be the positive value of x. So if x was 2, this would still be 2. If x was minus 2, this would still be 2. That's why our graph looks exactly the same when you reflect over the y-axis. Now, with other functions, it doesn't always look the same. If I give you a different function, say this function here, well, if I graph that over the y-axis, it turns into this. In other words, every point here is over here now. This point here is over to there. This point here is over to there. So if you have a more complicated function and reflect it over the y-axis, it does change. The problem here is that they're teaching you about transformations before they've taught you about curved lines. And it's curved lines that change the most when you reflect over the y and the x-axis as far as that goes. So this is a little bit of a difficult subject to cover when somebody has not been taught functions of curved lines. But we can kind of do it using the absolute value function. All right. Let's talk about the third type of transformation. This one here. Let me erase the others that I have written up here. Really, the best way to cover these is one at a time. Then you can cover them all put together, which is what you have to do. These questions they're asking you is, they're all in combination. Okay? But in order to figure them out in combination, you need to figure them out one at a time. Well, what does this one mean? What if I said to you, f of x is equal to the absolute value of x, that's our elementary function. What is f of x minus 2 equal to? If f of x is equal to absolute value of x, what is f of x minus 2 equal to?
2.
It's equal to the absolute value of x minus 2. In other words, remember what we do here when we have the f of x notation. We take whatever is in the parentheses and we plug it in for x. Well, if I plug x minus 2 in for x, I get this. That's all we do. It's really relatively simple. I know it's complicated looking, and if you're not used to the f of x notation, it can be intimidating, but it's not really. It's really quite simple. You really just need to memorize one thing. Whatever is in the parentheses, plug in for x. Okay? Now, if I gave you this function, the absolute value of x minus 2, you could graph it by knowing that we are going to move horizontally to the right by 2 units because h is a positive 2. So I would go over to 2 on the x-axis and my graph would now look like this. This graph would be f of x equals absolute value of x minus 2.
And David, did he get the 2 from where?
I just made it up. In other words, I made it up because the kind of problems he's going to have to answer are these kind. How would you graph this? Hold on.
Yeah, he might just put this. I mean, because
how would you graph that?
I'm glad you brought that up because I'm struggling with that. So
I'm sure. I know this is going to be confusing, especially if you missed the day where they covered it. So let's just take it one step at a time. So how would I graph this? If somebody gave you this as a problem, what would you think you would do? In other words, this is a variation on this. The question is what kind of a variation?
Would we start at x minus 7?
It would start at x equals 7, not minus 7. Remember, the format is f of x minus h. So when we were looking at this, we know that h is positive 7, which means move to the right by 7 units. So to graph that, I just move the vertex to the right by 7 units and graph it.
He's just using that as an explanation.
Yeah, in other words, it doesn't matter what the number is here. What we're trying to learn is what does this mean? That means you go this many units to the left, no matter what that number is. If it's 2, you go 2 units to the left, to the right, excuse me, sorry. If it's 3, you go 3 units to the right. If it's 7, you go 7 units to the right. What if it's plus 7?
You go 7 units to the left.
Yeah. In other words, if it's plus 7, then h must be minus 7. Because it would have been x minus a minus 7 giving you x plus 7. So if this is a plus 7 here, it goes, the vertex goes to minus 7. Okay? You with me?
A little bit. So when you're graphing any absolute value function like f of x equals x plus 7, you basically go to the vertex, which would be the number, like 7, 2, whatever, and you basically just
Draw your
draw
function.
a v.
Draw the original function, the absolute value of x function.
All right.
Okay? Now, let's talk about the fourth type of translation, which is if I have f of x plus some c outside the parentheses. And an example of that would be absolute value of x plus 3. Notice my plus 3 is not inside the absolute value markers, it's outside. In other words, if I said to you f of x is absolute value of x, what is f of x plus 3? That would be the answer. It would also mean, since we are in this format, that is a vertical shift. And we take our f of x graph and we move it up 3 units. Not left or right, but up or down. So if we look back at our 6 types, you understand reflecting over x?
Yes.
You understand reflecting over y?
Yes.
Do you understand horizontally shifting it left or right?
A little bit, yes.
Doesn't change the shape. It just moves it left or right.
Oh, all right.
Okay?
Yeah.
That's important because these last 2 change the shape. So these first 4 are the simplest. When I move it vertically, up or down, I do not change the shape. I don't change this angle here between at the vertex. In other words, if I move the whole thing up or down, all I do is take exactly the same function and move it up or down. And notice that that is accomplished when you have f of x plus c. You're adding some number outside the function. All right, let's look at the last 2, and then maybe we can review them in context of these 2 problems we have. I don't want to spend a whole lot of time on the last 2, although you do have some questions that involve those last 2. This one right here involves the last one, and this one involves it. So we can't not talk about them.
So what numbers are those, David? 36 and what, 37?
34 and 36
Okay.
are both involving transformations. All right, let's talk about the last 2 just so we cover them. Not to confuse you, but all right. If we have f of some number times x, in other words, remember f of x is always some elementary function. In our case, f of x is the absolute value of x. Well, this is a horizontal translation because it fits that format, right? In other words, I've got the x minus 2 inside the parentheses, just like this. And it translates to this. That makes it a horizontal translation. Now let's talk about what if I had f of 2 times x. In other words, I have a multiplier inside. Notice this one is an addition or subtraction inside. This is addition or subtraction outside. This is multiplication inside. This is multiplication outside. Each one of these things is different and will manifest itself differently when you look at the function. So how am I going to write this particular absolute value function? What is f of 2x?
4.
No. In other words, how do I write it? If f of x is absolute value of x, what is f of 2x?
2x.
The absolute value of 2x. Again, the only thing I do is I substitute 2x wherever I see x. It's kind of like, let's get just, in other words, f of x isn't always absolute value of x. In this case, f of x is this. Okay? More complicated. Now, if I said to you, what is f of 2x, what would you do?
You'd have 2x.
2x quantity squared plus what?
I'm not sure.
Plug in that wherever you see x. It's as simple as that. That's the only thing you need to memorize, is that if you're given a function in f of x terminology, and then they ask you what is f of something other than x, in other words, this time I'm saying f of 2x, I'm going to plug in 2x wherever I see x. That's the way you do it. If I said, what is f of 3? I'm going to plug in 3 wherever I see x. That's the beauty of the f of x terminology, is that you can then do things like, well, what is f of 2 of x? Or f of 3? So all you have to do is plug in whatever is inside the parentheses into x of the original function. So that's what all of these mean on the left. So when I'm looking at this fifth one here, horizontal stretch or squeeze, that's where you would have something inside. In other words, what they give you always is this. And they say, what's going on here? So I have to be able to go backwards. I have to say that if I'm looking at the absolute value of 2x, well, that must mean that I'm talking about f of 2x. And if I'm talking about f of 2x, I'm talking about a horizontal stretch or squeeze. If I look at the sixth one, the vertical stretch or squeeze, I'll get to what they each mean in a moment, but if I'm looking for something in this format, I would be looking at 2 times the absolute value of x. Notice that if somebody gives you this, that you know is 2 times f of x, not f of 2x. What does a horizontal squeeze mean? When you do horizontal stretches, squeezes, and vertical stretches, squeezes, you do change the shape of the curve. If I do a horizontal squeeze, it's like pushing on that end and that end, resulting in that is a horizontal squeeze. Okay? A horizontal stretch changes the shape also. A horizontal stretch would flatten this thing out. And not just this way, all of these are horizontal stretches, just by different factors, different numbers. So that's what a horizontal stretch or squeeze means. What is a vertical stretch or squeeze? Well, it looks very similar to horizontals when we're dealing with these kind of functions. Again, if we had more complicated functions, they are more easily illustrated. But basically a vertical stretch is this same thing, makes it skinnier. Notice that with this function, a vertical stretch is the same as a horizontal squeeze. A vertical squeeze flattens it. In other words, a vertical squeeze, you would push down on these two lines to flatten it. All right. So, let's see. Without belaboring that point, let's now look at the function that they're asking us about on 34. They say, well, what is being done to this function? In other words, we're multiplying it by a negative 1/3. Whatever the function is, they don't even tell us what it is. It's just some f of x. But we don't need to know what it is. In other words, if I look back at my list of what each is, look in where I've got the rectangle. This is the key part to memorize, is everything you see in this rectangle here and what it means on the left. Let's even erase all of this over here. In other words, I use the absolute value function to illustrate these various transformations, but it applies to any kind of function, whether it's linear, quadratic, absolute value, cubic, no matter how curved it is. All of these transformations apply. Well, the function they gave us was minus 1/3 f of x minus 5. There are three things that are being done to that function. Tell me what they are.
It's reflect over the x.
Good, that's first thing. And always do your reflections first. If somebody told you to graph this, do the reflections before you do the horizontal and vertical translations. What else is happening?
The vertical up or down.
Good. Vertical shift by what?
Negative 5.
So down 5 is how you describe that. Okay? And finally, there's one other thing going on.
I'm not quite sure what that last one is.
Okay, this 1/3 here. We're multiplying our function by 1/3. Outside the function, that fits that right there. You see why?
Yeah.
Last one?
Yeah.
Last one.
That is a vertical stretch or squeeze. Okay, this gets a little more complicated. It's a vertical stretch if this number is greater than 1. It's a vertical squeeze if that number is between 0 and 1. This is 1/3 between 0 and 1, so it's a vertical squeeze. Sometimes they call these scrunches. They both mean the same thing.
Hey, David, hold on just for a second. I want to make sure I get this straight.
Okay.
So what you're saying, as long as you have the equations down, that's what you're looking for, whether I have them accurately? Yeah, we do.
Pretty easy.
Yeah, and you've also, this is being recorded. I mean, you can go back and do it, but you've got those written down. Okay, David.
Okay. Now, let's, before the end of the session here, let's look at 36 and see what's being done. At 3 times x plus 3 minus 4. Hold on a moment. So we have 3 times the absolute value of x plus 3 minus 4. Okay? Before we figure out what's being done to this function in the way of transformations, what's the elementary function? What is f of x equal to?
3x.
No, the elementary function is the absolute value of x. And you have to know that to know what's being done to it. Because if the elementary function was 3x, it changes everything. In other words, you have to know what this is to begin. So if the elementary function is absolute value of x, what's being done to it? We have three things. We have this, we have that, and we have this. What does each of those mean?
We have horizontal left and right.
Which way?
Right.
Remember, a positive h means right. This is a negative h. This is the same as x minus a minus 3. Remember, we're using this right here as our general form. It has to be f of x minus h. Well, if I were to write this, I would write f of x plus 3. So we have a translation to the left, 3 units. What's the effect of this?
That's a vertical up and down by.
Which way?
And then that's down.
So it's
Down by 4.
down by 4. And finally this.
That's a vertical shift.
Stretch or squeeze?
Stretch.
Exactly. So if I wanted to graph that, we'll just end on that. Hold on. Well, as soon as I can get my thing on here, we'll graph it. All right. Always start with your elementary function. That is y equal absolute value of x. There's no reflections going on. We're trying to graph y equals 3 times x plus 3 minus 4. Is that right?
Yes.
Okay. So we can do these in any order we want. If there was a reflection, in other words, if there was a minus sign here, I'd do that first. But if there's no reflections, you can do them in any order. So what's the first thing we want to do? What were our 3? We were going left 3, down 4. Let's do both of those first.
All right.
So we go left 3. That would put it like that. And then we take that and move it down 4. Puts it like that. And the last thing is a vertical stretch by a factor of 3. So we know it crunches it up, but it crunches it up pretty severely. And there's your graph of that function. In other words, we don't need to plot a bunch of x and y points to graph this. What we need to know is what the elementary function looks like and how is this translated relative to the elementary function. And so we just do it one step at a time. We start with our elementary function and we do everything that's happening to it. Well, there's a lot of things that could happen to it. I could have something that looks like this. Notice that if I gave you this function over here, it has all 6 things going on. It's got the reflection about the x-axis, it's got the reflection about the y-axis, it's got the horizontal movement to the right of 4 units, it goes up by 6 units, it has a horizontal squeeze by a factor of 3 and a vertical stretch by a factor of 2. Now, I didn't say that backwards, that's true. When you're talking horizontal squeezes, it's when this number is greater than 1. It's a horizontal scrunch if this number is between 0 and 1. the opposite of the vertical stretch factor. The vertical is a stretch factor if it's greater than 1, and it's a scrunch or squeeze if it's between 0 and 1. Unfortunately, the way you always get presented these problems is they give you this function here and say what has been done to this function. In other words, they give you a function and it can be as complicated as you want, but you have to tell them what is being done to this function. Well, reflecting, vertically stretching, horizontally shifting to the right, and vertically shifting up. And that's pretty much the process you go through on each of these. All right, that's a great place to end. Coming up next is arithmetic sequences, and that's a whole other area.
Those are pretty easy.
Yeah, and then for the because it goes to sequencing, and then piecewise functions, right, which he's done. And then I think we got to send you one more sheet, which I'll do later on.
Oh, okay. I was wondering. Then, I thought it ended at 41. Okay.
No. Then you got 52. But what it is, David, is you probably can anticipate it. It's adding polynomials, subtracting polynomials, multiplying polynomials, or binomials. So we get into that, greatest common factor. And then...
sounds good.
Yeah,
that's a lot of math,
yeah,
but I think we'll have time to cover it in the allotted.
Because this one on, I'll tell you, this one on the transformations, this was one that he just glassed over, and the teacher told me that they just barely touch on it, and she said not to really worry that much about it.
Well, okay. I hesitated whether to spend as much time as I did, but given that they had 2 questions on it, and both of them required you to know in other words, this question here requires you to know the reflection, the vertical scrunch, and the vertical shift. So, like I said, this is an easier subject if you can deal with curved lines as opposed to linear functions, straight lines, or even the absolute value function didn't really illustrate it that well. But enough, I think.
All right, David. Well, we'll talk to you tomorrow then. Like I said, I'll shoot this 42 through 51, and I'll get it over you this afternoon.
Sounds good.
Bill up to date. See you tomorrow.
Okay. Bye-bye.
All right, David. Thank you.